Good morning. Can you hear me and see the screen?
Yeah, I can see it.
Okay, thank you. Do you have any questions from last time before we get started? I'll quickly review last week's lecture. All right, so last time we started introducing the concept of semiconductors, and we said that, as the name implies, these are solids which have a conductivity in between those of very good conductors like metals, or very bad conductors such as insulators, or you could express conductivity as the resistivity rho, where sigma conductivity is a reciprocal of the resistivity rho, which is what's shown over here. So semiconductors have a resistivity in between those of low resistivity metals and high resistivity insulators. Okay. But then we said that to really get a handle on the physics of semiconductors, you have to introduce a concept called energy band diagrams, which is what I sketched on the left-hand side of the slide. And we said that in semiconductors or insulators for that matter, according to the rules of quantum mechanics, the electrons in that solid cannot have any arbitrary energy, where in this figure, I'm plotting electron energy increasing upwards as a function of position in the semiconductor device. These are known as band diagrams, energy band diagrams. And we'll be using these to explain all kinds of devices. So you need to be very comfortable with band diagrams, okay? And of course, I'll explain that in much more detail in chapter 3. But for starters, we said that, okay, so they can have allowed energy levels in this lower band, which is shown shaded, where most of these allowed energy levels, allowed according to the rules of quantum mechanics, are filled up with electrons, and that forms what's called the valence band. And we saw that that corresponds to the energy levels of the electrons in silicon in the outermost valence shell when they form covalent bonds with four nearest neighbor silicon atoms. Okay. Then above that, we have a forbidden energy gap, which I call E sub G. So electrons cannot have any energy levels in those energies. But then above that, you have another band of allowed energies known as a conduction band, the bottom of which I denote as EC. The top of the valence band is E sub V. Okay. Now the conduction band normally is going to be almost completely empty. In an insulator, the band gap is very, very large. In a semiconductor, it's more modest. In a semiconductor, the band gap's of the order of 1.1 electron volts in the case of silicon. In an insulator like glass, that band gap might be 9 electron volts. Because the band gap is so much larger in an insulator, you cannot thermally excite electrons from the full valence band across this large energy gap into the conduction band. So an insulator has a totally full valence band, totally empty conduction band, and such a material does not conduct current. Now, why? Well, to understand that, we use an analogy of water bottles that are completely filled up with water in the case of the valence band and completely empty in the case of the conduction band. And we said that a completely empty band, if you move it around in the gravitational field, obviously would not lead to any net motion of water from one end to the other. Similarly, a completely full band corresponding to the valence band also would not give rise to any net motion of water. I mean, water molecules may move from one side to the other, but they'll dislodge other water molecules and there'll be no net flow of water. Similarly, a completely empty conduction band does not give rise to current flow, even if you apply electric field to it. And this is the harder part to understand. A completely full valence band also does not give rise to current flow. When electrons move in the electric field trying to gain energy, it has to dislodge other electrons to a lower energy state, and there's no net motion of the electrons, okay? That is due to a principle of electrons that you may have heard of in chemistry, known as the Pauli exclusion principle. So we'll clarify that later on, okay? All right, now, on the other hand, in semiconductor, where the band gaps are more modest, at room temperature, which is 300 Kelvin, you have a so-called thermal energy, KT, K being the Boltzmann constant, T is 300 Kelvin at room temperature. That's about 25 milli electron volts, okay? Now, that's smaller than the band gap in silicon, which is 1.1 eV, but not that much smaller compared to an insulator. So now a few electrons can be excited thermally from the valence band into the conduction band. And in the process, they create mobile electrons in the conduction band, which move opposite to the electric field. And they leave behind empty states in the valence band, which are known as holes, which behave like positively charged carriers. And the analogy that we use using the water bottles is now you take a few drops of water from the full bottle, move it up into the empty bottle, you form these droplets of water, leaving behind bubbles, which are like here, holes. Now in gravity, of course, the water droplets would move downwards to the lowest energy state, while the bubbles would move upwards in the bottle also to the lowest energy state. So for whole energies or the bubble energies, the energies increase downward, while the electron energies or the water droplet energies, the energies increase upwards in this particular figure, okay? So that picture then explains why you have this exponential dependence on temperature of the conductivity, because as you increase the temperature T, the number of carriers that are excited increase exponentially as e to the power minus this band gap Eg over 2 kT. So that gives you the probability of excitation. Okay. Now, similarly, the semiconductor conductivity can be increased with electromagnetic radiation, provided the photon energy h nu is greater than the band gap, because then, once again, it can absorb electrons in the valence band, absorb energy. Electrons in the valence band can absorb energy and be excited thermally, excited by this electromagnetic radiation into the conduction band. On the other hand, if the photon energy is less than the band gap, it just passes straight through. Okay. And we use that to explain why, for example, glass is transparent, because in the case of glass, the band gap is about 9 electron volts, much, much greater than the photon energies in the visible part of the electromagnetic spectrum. So none of those wavelengths are absorbed by glass, and that's why glass is transparent. On the other hand, if you have a low band gap material or a zero band gap material, such as metals, the light would be absorbed by that, and that's why metals are opaque. Okay. Now, this band picture also we saw had a correspondence in terms of chemical bonds. And to explain that, we have to look at the chemical structure of silicon, which in the periodic table is seen to be in column 4 of the periodic table. The column tells you how many electrons you have in the outermost shell, the so-called valence shell. In this case, it's the third shell in the case of silicon. Now, of the 4 electrons, 2 go into the 3s2 state and 2 go into the 3p2 state. But remember from chemistry that in the p subshells, you could have up to 6 electrons. So the outermost shell would like to have 2 plus 6, or a stable octet of electrons. But in this case, it only has 2 plus 2, 4. Now, the core electrons in 1s and 2 levels don't really play much role, either in chemistry or in semiconductor physics. Okay. So because the silicon atom has 4 electrons in the outermost shell, it tends to form a crystal structure in silicon, a so-called diamond structure, which we'll talk about in more detail today, where each silicon atom is surrounded by 4 nearest neighbor silicon atoms, making a nice symmetric tetrahedral arrangement, where each of these covalent bonds is made up of 1 electron from this atom, 1 electron from the neighboring atom, and so for the other 4. So now, because of these 4 covalent bonds, each silicon atom effectively, on average, has 8 electrons surrounding it. That gives you the stable octet of electrons. Now, such a scenario corresponds to the valence band being completely full, where all the covalent bonds are intact. But if you thermally or by radiation break some of these covalent bonds, then we saw that if you break one of these bonds, you'd have an electron which moves opposite to the electric field, and what's left behind if you break one of these bonds, you get an electron which moves opposite to the electric field, and what's left behind is a hole which moves in the direction of the electric field. So hopefully you see the correspondence between the energy band picture and this chemical bond picture. Okay. You can then extrapolate those ideas to compound semiconductors such as gallium arsenide, where gallium has 3 electrons, arsenic has 5. So once again, 3 plus 5 makes 8. But now the bonding is partly covalent, partly ionic in character. Okay. So we said that although you could have semiconductors in different states of matter, the most high performance devices are made in single crystal semiconductors. A single crystal structure is shown in a cartoon view in this left-hand figure. Amorphous materials, on the other hand, are shown in the middle, where these atoms, as shown, have no periodicity. They're kind of random, while in single crystal, they have short range and long range periodicity. On the right-hand side, I'm showing something intermediate, which is called a polycrystalline material, where I'm not showing individual atoms anymore, but rather I'm showing these planes of atoms, like these lines. So what's shown over here in a cartoon view is you have these small regions, which are called grains, where you have this nice periodic arrangement of the atoms making these planes, but the neighboring grain has a different orientation. Okay. So we said that in an IC, integrated circuit, all classes of materials are used, but the guts of the action are in a single crystal semiconductor, typically silicon or maybe gallium arsenide and things like that. So we want to spend today discussing the mathematics of single crystal structures, because that'll be very important later on to understand electronic properties of these solids. Okay. So where we left off last time is saying that to describe a crystal mathematically, you have to introduce a concept called a lattice, which is just an abstraction and refers to an infinite periodic arrangement of points in space. Look at these terms that are shown in italics. So it has to be infinite in extent for it to be a true crystal, and it has to be periodic arrangement. So in this particular example, it's a square arrangement of points in space. Now, it need not have any atoms at this point over there, okay? So it's just an arrangement of points that makes the lattice. Then at each of these lattice points, you put something physical, which in this case could be, say, a single black dot, could be an atom, for example, or it could be a group of atoms, okay? As we'll see later on. And that physical object, either a single atom, as indicated in this figure, or perhaps a group of atoms, that's known as a basis. And if you do that, if you put a basis at each of these lattice points in the same spatial orientation, you end up with what's called a crystal. And that's something that you can hold, okay? Now, if I look at this definition of the lattice, which underlines the definition of a crystal, you immediately see that, from a practical point of view, no structure is going to be infinite in extent, right? So as such, any finite object will have defects at the surface, which are known as surface states. And we'll come to that later on when we start talking about devices. We'll see that surface states play a very important role in semiconductor devices. Okay, you have to really know how to handle the defects that you have in a practical crystal, which will always be bounded by surfaces. So no practical crystal will be a true infinite structure, obviously. Question? Okay. All right, so the previous example showed a very simple structure, a square arrangement of points, and we put, say, a single atom in that basis, okay? Now, the thing about lattices is it's really the symmetry of those points which determines the lattice, okay? Additional degrees of symmetry are given new names, okay? So in this case, a square arrangement of points will lead to a square lattice. On the other hand, if instead of a square arrangement of points, suppose I put these points in the form of a rectangle, I'm showing only one of these units over here, where these dimensions A and B are not equal to each other, but this angle is still 90 degrees, as in the case of a square. You can say that, okay, now a square is obviously a special case of a rectangle, but because a square clearly has additional symmetry compared to the rectangle, you give it a different name. You call this a square lattice, while if you had this, where A and B are not equal to each other, you call that a rectangular lattice. So it's a symmetry that determines the lattice type, not the magnitudes of the distances. So in the case of the square lattice, if the distance between these 2 points was 1 angstrom versus 13 angstroms versus 2 miles, doesn't matter, they're all square lattices, okay? Now, the reason I'm harping on this concept of symmetry is because you'll see later on that then plays an important role in the electronic properties and the device properties, okay? Now, moving on, it turns out people have figured out the number of different symmetries that are possible in 2-dimensional structures. We live in a 3-dimensional world where we'll see there are 14 different types of symmetries, but it's easier to visualize things in 2D to start off with. So here I show another example where these atoms are arranged in a way where A and B, these are known as your primitive vectors, are different from each other, and plus this angle between A and B vectors is not 90 degrees, as in the previous example. So now this region ODEF, highlighted in blue, forms a rhombus. So that's why it's called a rhombic lattice. Now you might say that, a square or a rectangle are special cases of a rhombus. So why are we giving special names to a square or a rectangular lattice, right? Now, clearly, from a geometric point of view, a square has additional symmetries compared to a rhombus. And it turns out that then leads to more interesting electronic properties compared to, say, a rhombic lattice. We'll clarify those things later on, okay? Now, some definitions are important. So in this particular case, the most fundamental building block that we talked about is a so-called primitive cell, which is described as the most fundamental unit which can describe this lattice structure, where you can translate this primitive vector by integer numbers of these primitive vectors. You can translate this primitive cell by integer numbers of primitive vectors, say m times A plus another integer n times B, to go from ODEF to say another position, O prime, D prime, E prime, F prime, right? So to do this, what do I have to do? In this case, obviously, along A, I have to go by 1, 2, 3, right? 1, 2, yeah, 3. And in this direction, I have to go 2, right? So I have to go 3 times A plus 2 times B to go from O, D, E, F to O prime, D prime, E prime, F prime, right? Now, obviously, you can see that for different choices of M and N, you could cover this entire lattice structure. You wouldn't miss any points, and you'd also not have any additional points. So that's what the fundamental primitive cell tells you, okay? Now, how many lattice points do I have within the primitive cell? So let's count, say, O prime, D prime, E prime, F prime. You might say that, oh, I have 4 lattice points. No, you actually have 1, because each of these in this particular example are shared amongst 4 other rhombuses, right? So for each of those, you should count only 1/4 of them as belonging to this primitive cell. So 1/4 times 4 gives you 1 lattice point. And that, in fact, is a theorem that you can only have 1 lattice point per primitive cell. Not atoms necessarily, because the bases that you put on those lattice points could be more than 1 atom, okay? We'll see in the case of silicon, that happens to be actually a basis of 2 silicon atoms. So far, we are still talking about lattice points. Now, the other concept that we just introduced at the end of the last lecture was the concept of a unit cell, okay? So in the case of a unit cell, now look at this larger rectangle, PQRS, which forms a rectangle, okay? Now, you have to agree that a rectangle is a more geometric object than a rhombus, and it's going to be easier to do math in terms of rectangles or squares compared to a rhombus. So it turns out in many cases in nature, if I'm willing to relax my definition and not work with this most fundamental primitive cell, but if needed, a larger unit called the unit cell, which may be more symmetric, I choose to do that because then my life gets easier. Okay, and it so happens that for the common semiconductors, you have a larger entity called the unit cell, which is in our case going to be a cube, and I'd much rather deal with a cube rather than some oddball object, which is the primitive cell. We'll see that in a second. Okay, so what am I giving up by going to this larger entity? So now I can have more than 1 lattice point per unit cell. So as shown over here, I have lattice points not only on the corners, but I have an additional lattice point in the center of the unit cell, shown as T, right? So how many lattice points in this unit cell? The 4 corner ones times 1/4, that gives you 1, plus the 1 in the middle. So a unit cell can have more than 1 lattice point, and I'm allowed to have lattice points not only on the corners, but also in the center of the face, or if it's a 3-dimensional object, in the middle of the body of the unit cell, okay? Once again, I'm still talking about lattice points. The basis, that depends on the crystal that I'm looking at, okay? So it could be a single atom, or in many cases, it could be a group of atoms. The one final thing that I want to add is these concepts of primitive cells, which is this most fundamental unit block with 1 lattice point per primitive cell, is not a unique concept, okay? In fact, you can have many definitions of primitive cells which are just as valid. So for example, I could have this more sloping rhombus, which is also a valid primitive cell. Okay, so now I have this vector and a longer vector over here, which forms a primitive cell. You'll see that it still has 1 lattice point within this more sloping rhombus, okay? Although you have actually an infinite possibilities in terms of primitive cells, the convention is to choose the simplest one, defined as the shortest primitive vector A and the next shortest primitive vector B, as shown on the left-hand side. So that's the definition that we'll be sticking with. And we'll choose primitive cells with the lattice points on the corners, though that also, you have some flexibility. You could, in principle, have chosen a primitive cell like this, where that lattice point happens to be in the center. So that's also valid. But in this class, we'll draw them with lattice points only on the corners of the primitive cell. Okay? Any questions? So all of that was a review of the last lecture. All right, so we live in a 3-dimensional world, and a guy called Bravais, a French physicist, figured out the possible symmetries, not the distances between the lattice points, the possible symmetries that you can have in 3D. And believe it or not, there can be only 14 different types, no more, no less. Now, we won't look at most of them. They're very complicated in some cases. We'll only focus on the ones that are relevant to semiconductor devices. And it so happens Luckily for us, the common semiconductors exhibit the most simple kind of symmetry, a cubic symmetry. Now, within the cubic class of symmetries, there are three sub cases as shown over here. Okay, so this absolute simplest case is a simple cubic cell, which is shown on the left-hand side, where I only have lattice points on the corners of the cube, nowhere else. How many lattice points do I have in this cubic cell? Well, I have 8 corner points, but remember, each of them are surrounded by neighboring cubes, right? So now you have to think in 3D, okay? So if I focus on this one, for example, I have, 4, I don't know if you can visualize it. So you'll have 4 cubes in the upper plane, and then below you'll have 4 more cubes, right? So there's 8 cubes adjoining this point. Can you visualize that? So only 1/8 of this point should count towards cube, and have 1/8 times 8, or 1 lattice point within the cube. Once again, that fundamental property of the primitive cell, okay? But it turns out there are more complicated cases with a cubic type of unit cell. Now I'm going to this larger entity, the unit cell, rather than the primitive cell. So here, in this body, so-called body-centered cubic unit cell, I'm allowing lattice points not only in the corners, but also in the center of the body. And then finally, on the right-hand side, you've got the face-centered cubic cell, lattice points not only in the corners, there's nothing in the center of the body, but I have 6 lattice points in the centers of the 6 square faces. That's known as a face-centered cubic cell. Now, I want you to pay extra special attention to this because the most common semiconductors have this kind of a unit cell. Now, the question is, are these the more fundamental primitive cell? And the answer is no, because I've allowed additional lattice points, right? In addition to the ones at the corner. So how many lattice points do I have in the case of the body-centered cubic? I have 2, because I got the 8 corner ones times 1/8. So that gives you 1, plus the 1 in the middle, which counts fully, right? How about for the FCC? I got the 8 corner ones times 1/8, plus the 6 face-centered ones, but only half of them should count, right? Because this one is shared between this cube, and there's another cube on the right, to the right of that, okay? So here, I have 4 lattice points, okay? Now, if you ask me to draw the more fundamental unit primitive cell, it's a very strange-looking geometric shape. I'm not sketching that, but if you look at it in textbook, you'll see they have very oddball shapes. That kind of explains why I'd much rather work with these larger unit cells, okay? Now, to describe crystals mathematically, you very often have to have some sort of a notation to describe different crystalline directions or planes in a crystal, okay, to do math. Now, one way to do that would be every time to, kind of have a cartoon sketch or one of these crystal structures, and then, point out the direction on the structure and the planes. You could say, draw a plane like that, and you can say that, like, I want to refer to this particular plane or this particular direction. Now, clearly, that's a very clumsy way of doing it. There's a shorthand notation known as the Miller index notation for planes. And in the next slide, I show the Miller index notation for directions that we'll be using, okay? So how does it work? It's very straightforward in the case of the cubic crystal system, which is the special case that we're interested in. So the recipe is as follows. You set up an XYZ coordinate system where you choose the origin and set it at one of the lattice points. Which one? It doesn't really matter because of the symmetry, all lattice points are equivalent. And then you align the axes XYZ to line along the edges of the cube as shown in the middle over here, okay? And then if I'm interested in the Miller index of a plane, say this blue one shaded in this particular example, just as an example, what I do is I determine the intercepts of that particular plane with the 3 axes in terms of multiples of the unit cell dimensions, okay? So the size of the cube, suppose I call that A. A, by the way, is known as your lattice constant, okay? So if I go back to the previous example, A is your lattice constant, okay? Now you'll notice that A is the distance between the nearest neighbor silicon atoms in the case of the simple cubic cell, but not in the case of, say, the FCC or the BCC. So when you hear lattice constant in this class, it doesn't refer to the nearest neighbor distance. It's really the side of the cube. We'll figure out later on what that closest distance between nearest neighbors are in just a second. I'll do some problems today. Okay. All right. So you determine the intercepts of the planes in multiples of the unit cell edges. Okay. So what are the intercepts of this particular plane along X, Y, Z? If I write X, Y, Z, it is cutting the Z-axis at this location at a distance of A, right? But this plane is parallel to the Y and the X-axis. What are the intercepts? It doesn't cut the X-axis, so the intercept is infinity. Doesn't cut the Y-axis, intercept is infinity. So the intercepts are infinity, infinity, and A along X, Y, Z. Next step is to take the reciprocals of those. What is reciprocal of 1 over infinity? 0, 0, 1 over A. And then finally, you reduce them to the lowest set of integers. So in this case, I multiply throughout by A, and I get 0, 0, 1, and I enclose them in parentheses as shown over here. So the Miller index of this particular plane is 0, 0, 1. Okay?
I have a quick question.
Yes.
Wait, how did you know that the X and Y were infinity?
Because this plane is parallel to the X-axis. So where does this plane cut this X-axis? Imagine this plane being extended all the way, right? It never quite touches the two parallel lines never meet, right? So if you have a plane which is parallel to this line, it'll never meet also. That's why he said that the intercept is infinity.
Okay, thank you.
Yeah, okay. All right, so that's one example. Okay, now let's look at this particular plane, for example. What are the Miller indices of those? Well, the intercept now along X is what? A. Intercept along Y, infinity. Intercept along Z, infinity, right? So you take the reciprocals, I get 1 over A, 0, 0. So the Miller index of this plane is 1, 0, 0. Okay? Now, although these two planes, 0, 0, 1 and 1, 0, 0, are different, obviously, yet clearly they're sort of similar, right? And you can kind of see that they're similar because I could have taken this cube and I could have rotated the thing by 90 degrees, as shown over here, and this top plane maps onto this plane, right? So remember we talked about the idea of symmetries. So in the case of the cubic system, what are the kinds of symmetries that you can have? Well, you could take a cube along this axis, say Z, and you can rotate it by 90 degrees. It maps onto the same lattice, 180, 270, and then 360 are back to the origin, right? So those are examples of rotational symmetry. You could also have other kinds of symmetry. You could look at this plane down below between the origin, this point, and this point. And if you reflect everything above, around that mirror, this sort of point goes down below, the ones down below come above, and hopefully you can see that you have mirror symmetry, right? So we'll talk about this later on also, and we'll see how these then play an important role in the electronic properties and the transistor properties later on. Very, very interesting, okay? But for now, I just wanted to make a point that this 001 and 100 plane, although they're different, they're kind of equivalent, and equivalent planes are denoted with curly brackets like this, 100 set of planes, okay? Now, one more thing before I leave this topic of Miller planes. Suppose I was to look at a plane on this side, okay, which cuts it along the negative axis, along, say, minus A, but it's parallel to the other two planes. What will be the intercepts? It will be minus A, infinity, infinity. I take the reciprocals. I get minus 1 over A, 0, 0. Reduce it to the lowest set of integers by multiplying throughout by A. So I get minus 1, 0, 0. The convention is to show the minus on top of that number. Okay? So a plane like this would be denoted as 1 bar 0, 0. That's a convention. Okay, that's also equivalent to this 100 plane. So that also belongs to the 100 set of planes. All right. One other quick example. So suppose I looked at a plane like so. Let's look at a plane like this, say, along the diagonal. I don't know if you can see it very well. So I'm drawing a line along the diagonal of this square, diagonal over here and see what the intercepts are. So what are the intercepts of this particular plane, which goes along the diagonal? Well, it cuts the x-axis at, someone help me out,
A,
A.
y-axis at
A,
A, and z-axis at
infinity.
infinity. I take the reciprocals. So what will be this plane be? It'll be 1, 1, 0, right? So for homework and exams, you have to be able to derive these Miller index planes, okay? Now, suppose I had a plane which was intersecting not at A, but at 2A, okay? So then instead of A, that cuts it at 2A, but then when I convert it to the lowest set of integers, that also gives you a 0, 0, 1 plane, okay? All right, so that's the notation for planes, Miller index notation for planes. There's a similar recipe for directions, very similar. So once again, you set up the X, Y, Z axes. Oh, one other thing that I might add. So suppose I want to get the Miller index for this particular plane, which cuts through the origin. Then the intercept would be 0, right? And the reciprocal of that would be infinity. You don't have to freak out. All that you need to do is just shift the origin to a neighboring lattice point so that the intercepts are non-zero, and you'll get the right answer.
Really quickly for the intercepts, can you have a negative intercept, or are all the values always positive?
No, you have a negative intercept in this particular case, right?
Yeah.
Yeah.
So,
So that
does
negative
that take an
intercept,
absolute value, or?
no. So the convention is that minus sign you put on top of the number. So you call that 1 bar 0, 0, as shown over here. Okay.
Okay,
So
so in the instance we just had where it was like the plane at the corner,
Mhm.
why would that intercept at y instead of negative y? Unless the direction heading toward us is just negative y, or not ya instead of negative a.
So you could do that. So you know, that's why this concept of equivalent planes matters. Okay. So whether the plane cuts at plus a or minus a doesn't really matter. Okay, because remember it's an infinite system. Okay. So as long as the same set of planes shown by these curly brackets 1, 0, 0, the properties will be the same. Okay, so that's a particular specific plane doesn't really matter. Okay, as long as it's equivalent to similar planes, parallel planes.
Okay.
Okay. Okay, so what is the recipe for directions? Okay, very similar. You set up an X, Y, Z axis, origin at one of the lattice points. Which one doesn't matter, they're all equivalent. Line up the axes along the edges of the cube. And then if I'm interested in a particular direction, you draw a unit vector. Sorry, along that direction, and you reduce the components of the unit vector to the lowest set of integers. Okay. So for example, if I look at this vector A, shown over here, of magnitude A, say, to begin with, the component along the x-axis is A along the x-axis. Component along the y-axis is 0. And along the z-axis is 0. You then reduce that to the lowest set of integers. And now that direction becomes 1, 0, 0. But to indicate directions, you enclose them within square brackets as shown over here. For planes, that was indicated as parentheses, equivalent planes with curly brackets, but directions with square brackets. Similarly, here also you can have equivalent directions. So the B direction, for example, it's 0, 1, 0, but clearly that's equivalent to 1, 0, 0, because, remember that symmetry thing that we talked about? You could have rotated this cube by 90 degrees along the z-axis, and then B maps onto A, right? So equivalent directions, the notation is to use triangular brackets like this. Now, in this class, I want you to be finicky about where to use parentheses and square brackets and so on and so forth, depending on the problem. If you use the wrong symbols, I will take off a couple of points in the exams, okay? Because you need to be, consistent. Let's do another example. Let's look at the direction along the diagonal, okay? Now, all that I need to do is to draw a vector, get the components along X, Y, Z, and then reduce that to the lowest set of integers. Now you can do if I chose a diagonal, you could get the actual components using trigonometry. But for simplicity's sake, we don't even need to do that in this particular case, because clearly from symmetry, I know that the components along X, Y, Z have to be similar, right? So let's call them alpha, alpha, alpha. You can figure out the exact value of alpha if I knew what these angles are and all that. I'm being lazy, I won't do that. If you convert that to the lowest set of integers, you divide through it by alpha, you get 1, 1, 1 through square brackets, okay? So I'll give you some homework problems where you'll get a chance to, work out Miller indices, and in the exams also be prepared to work those out, all right? Okay, so far we've said on the lattice points, you're free to put in a basis, which could be a single atom or maybe a group of atoms, where the group of atoms is called your basis. Now, so far, all the cartoon views have shown single atoms in some sense, okay? Now, we're going to a more complicated scenario, which is what we have in semiconductors, where I start with an FCC lattice, and at each lattice point, I don't put a single atom, but I put two atoms, the one shown in blue, say, and then another atom in the base is shown in this gray circle shown over here, okay? So both of these atoms, this blue atom and this gray atom, are associated with this lattice point in the corner. But if I do that, I have to do the same thing at every single lattice point. So here is another lattice point in the face center of the square, blue atom, and I put the black atom of the same basis in the same orientation. What is the orientation that I'm talking about? In this particular example, I go along the edges of the cube by 1/4 the side of the cube. So if the lattice constant is A, I go along the x-axis by A/4, along the y-axis A/4, and then z-axis A/4, okay? I have to do the same thing at this lattice point. I'm showing that for a few other cases. I'm not showing it for all the lattice points. Do not clutter up the figure. So if you did that, and you now looked at the arrangement of the atoms, not the lattice points, you get a picture as shown in the lower figure. Okay, so I have, for example, an atom at the corner of the cube, and I go A/4, 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 I get the second atom. So both of these form the bases associated with this lattice point. I do the same thing everywhere. Okay. Now, another way of doing the same exercise, I'm just saying the same thing in a slightly different languages. You can say that, okay, I start with one FCC lattice. I put the first atom in the lattice at those FCC lattice points. What is FCC? Is this particular case that you showed, where I have lattice points on the corners of the cube, but I also have additional lattice points on the 6 square faces. That's why it's called the face-centered cubic lattice. I don't have any lattice point in the middle of the cube, this body-centered point, okay? So this is the one that I'm looking at. Like I said, this is the most important case because most common semiconductors belong to this face-centered cubic unit cell, okay? So what I'm doing now is I'm putting in the first atom of the basis at these points, but then the second atom is displaced by A/4, A/4, A/4. So you can kind of visualize this as taking a second FCC structure and displacing the whole structure by A/4, A/4, A/4 along XYZ axis, right? And if you do that, lo and behold, what you'd end up with is something like this, where now these are actually the atoms themselves, okay? So this is the first FCC lattice locations. And this one, for example, is when I've displaced it by, A/4, A/4, A/4. So similarly for here, that's the face-centered cube location. I go A/4, 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 I come to this. All right.
So do you
Yes.
just place, so like normally in the one you showed above, it had a atom in each of this like center of the 6 faces, but do you just
Mhm.
place one here and then place all the other atoms
So
1
for
over
each,
4 from that?
so you start out by putting in one atom at the FCC points, which would be the corners of the cube and the square faces, okay? And for each of those, you have to put in a second atom displaced by A/4, 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 okay? I'm not showing all of them in the top figure to not clutter up the figure, but I'm showing all of them in the lower figure, okay? Where I'm now showing all the individual atomic locations.
So I'm not completely sure what the point of like why is there a difference between the black and the white atoms, or is it just showing that there's a second square
It's just showing the second
inside?
square. Yeah.
Okay.
Oh, in the lower figure, you mean?
Yeah, the lower figure.
Oh no. So in this particular example, they're all the same color. What the point of showing the black atoms is showing the more fundamental unit that I'm going to come to in just a second. But down below, if this was a silicon crystal, think of them as all being of the same color. Okay, all black or all white.
Okay, so you put like all the atoms and all the faces and all the corners, and then you just have as many atoms as you can, 1/4 A from those, and that's all you do to get the structure.
Right, not
I
as
think
many
the
atoms.
thing that's just confusing me is that it looks kind of asymmetrical almost on the inside.
Yes, it is asymmetrical. So that's a very good point. I'm glad that you observed it. So if you look at this lower figure where I'm showing the individual atomic locations now, it is asymmetrical, right? So it doesn't meet the definition of a lattice where you have to have symmetry, right? Because you can kind of see that these dark regions, the atoms are kind of closely spaced together, but the other regions, say over here, but this seems to be a big void, right?
Yeah.
So you cannot think of each of these individual atom locations themselves as corresponding to lattice points. So that's a very important point. I'm glad that you brought that up. Okay, I was going to elaborate on that. On the other hand, if you look at the FCC structure, you'll see that they indeed have the same symmetric arrangement in space. Now here, of course, I'm just showing a single cube, but if you extended that in all directions, okay, you'd find that each of these lattice points would have exactly the same symmetric spatial arrangement in space. But once you put the second atom in the basis, things get a bit confusing because now you have to sort of look deeper, if you will, right? And not get confused by the locations of the atoms themselves with the location of the lattice points. Okay, so this atom and this atom in the basis both belong to, say, this particular lattice point. Okay, you can't think of both of these as belonging to separate lattice points, because if you do, then like you pointed out, the structure doesn't look very regular, right? Because then you have certain regions where the atoms are more close together and certain regions where they're big voids and things like that. Okay.
Okay.
Yeah, so let me go a little bit further, and then if you have more questions, I'll address that. Okay, so what I was going to say is, if you did this exercise where you start with the first atom of the basis at the FCC points and the second atom in the basis displaced by this 1/4, 1/4, 1/4 of the unit cell, you end up with the figure down below where I'm now showing the actual atomic locations. Okay, and if you did this exercise, you'd find something very interesting, and you have to just take my word for it. And what you'd find is each atom is going to be surrounded by 4 nearest neighbor atoms, making the same bond lengths and the same bond angles of 108 degrees. And such an arrangement is known as a tetrahedral arrangement. The term tetrahedron means you put an atom in the middle of a tetrahedral pyramid, say, and it's surrounded by equilateral triangles, 4 equilateral triangles. So you put an atom in the middle, and then you put atoms at the corners of the tetrahedron, and you join them by bonds, okay? And you'll find from simple trigonometry that the angle works out to 180 degrees, and these distances are all the same. That's what you'd find if you did this exercise of an FCC and displaced by 1/4, 1/4, 1/4, okay? Now, this structure sometimes, colloquially and erroneously, is called a diamond lattice. And this goes back to the very important question that was raised a few minutes back, okay? Why is it called a diamond lattice? Because if these atoms all happen to be carbon atoms, that's what diamond is. Okay, but as you just pointed out correctly, you shouldn't really call it a lattice, because if each of those points of the atoms corresponded to lattice points, it doesn't meet this requirement of being perfectly symmetric in space. Okay, so really you should define that as an FCC lattice with a basis of 2 atoms, say 2 carbon atoms in the case of diamond, or if it's 2 silicon atoms, that would be a silicon crystal, or 2 germaniums, that's a germanium crystal. Okay, but once you are clear about this in industry or in R&D, people will loosely call this a diamond lattice, because you kind of know what you're talking about. But strictly speaking, the diamond structure is not really a lattice structure. It's really an FCC with a basis of 2 atoms. Okay. So if all of these atoms are identical, say all silicons, all of these are called diamond lattice type structures. Okay. On the other hand, you could have a scenario where this atom maybe is a gallium and the nearest neighbor atoms are all arsenics, say, like in gallium arsenide. Okay. Those sort of structures are called zinc blende structures, as I mentioned in the last lecture. Okay. Because zinc blende is a mineral in nature where these interleaved structures, the 2 FCCs are made up of 2 different types of atoms. So you got the diamond where everything is the same kind of atom, but if these interleaved structures are made up of 2 different atoms, those are called zinc blende lattices. Okay. But once again, it's strictly speaking wrong to call it a diamond lattice or a zinc blende lattice. If you want to be finicky, you call both of them FCC lattices. In the case of diamond, then put 2 atoms on the basis of the same type. In the case of zinc blende, the 2 atoms on the basis are of different types. Okay. Now it turns out this underlying lattice structure is a natural outgrowth of the electronic structure that we talked about. Remember, we said that each silicon atom has 4 electrons in the valence shell. Similarly, this silicon atom has 4 electrons in the valence shell. So therefore, they share 2 atoms to make a covalent bond. And you're making these 4 covalent bonds, making this nice symmetric tetrahedral arrangement in space. And the network continues like that. Okay. And as a result, this silicon atom has basically, on average, a stable octet of electrons around it. Similarly, the neighboring silicon atom also is surrounded by 4 nearest neighbor silicon atoms, also has a stable octet of electrons around it. Okay. And that's how the whole crystal structure is held together in place. Now, question: now, if all these bonds were intact, would such a semiconductor be electrical conductor or an insulator? Anybody?
Can you repeat the question?
If all these covalent bonds were unbroken, if they're intact, would such a semiconductor be able to conduct electricity, or would it behave like an insulator?
An
Would it
insulator?
behave like an insulator?
Excellent.
Because it can't take
yeah.
any more electrons.
Yeah, because all those states in the valence band are full of electrons. Okay. And if they kind of move from one location to the other, because of the Pauli principle, they would swap and there would be no net motion of the electrons. Okay. On the other hand, at high temperatures, you could break some of these bonds. Okay. And then you'd have electron moving opposite to the electric field. So this electron would move in this direction. And what's left behind, a broken bond, would behave as a hole, which moves in the direction of the electric field. Okay. All right. So next, I'll work out some problems, the next 3 slides. And these are the types of problems that you can expect in the homework or exams. All right. So these are 3 worked out examples, and they're very important worked out examples. All right. So the first problem that I want to calculate is determine what's called the size of an atom based on the crystal structure. And from that, another concept called the packing fraction, how tightly packed these crystal structures are and what fraction of the space is empty space, not occupied by the atom. So these are typical things that you want to find out about a crystal. Okay. And we'll do our calculations for the case of the diamond structure or the silicon structure, because that's what you're interested in, or gallium arsenide, zinc blende type structures. Okay. So let's start with the diamond structure where all these atoms and the bases are the same. So I put the first atom at the corners and then the face-centered points, and the second atom in the bases. So both of these are associated with, say, this corner lattice point. And you have to do the same thing at every lattice point in the same orientation. Go A over 4, A over 4, A over 4. Okay. And if you did that, like I said, you'd end up finding that each atom is now surrounded by 4 nearest neighbor atoms, making the same bond angles and bond lengths and so on and so forth. Now, the problem that I want to calculate is, from this structure, if I knew what the lattice constant A was, can I calculate the size of a silicon atom? Let's say this is a silicon atom. Okay. In the case of silicon, lattice constant happens to be 5.43 angstroms. You can measure that experimentally through things called X-ray diffraction and things like that. Okay. So if I knew that lattice constant, can I calculate the size of a silicon atom? Now, the size of an atom is a little bit of a fuzzy concept, because if you remember your freshman physics, remember that an atom is mostly empty space, right? It's got this very heavy nucleus made up of these positive protons and the neutral neutrons that contains 99.9% of the mass. And then you have these electrons, negative electrons, whizzing around in these various Bohr orbits, the core shells, and then finally the outermost valence shell, right? So 99.9% is really empty space. But we'll pretend that an atom is a solid sphere. And the reason this atom and this atom are that far apart are because, although I'm not showing it that way, we'll pretend that they're that far apart because these two solid spheres are touching each other, okay? So that's a picture that we're using to calculate the size of a silicon atom, the radius, okay? How can I do that? If I knew this lattice constant A. Well, if for the basis I go along these axes by A over 4, A over 4, A over 4, can you tell me what the Miller index of this direction would be, joining the centers of these two atoms and the bases? You'll be going along the diagonal of the cube, right? And that's one of those 1, 1, 1 directions, remember? All right, so I want to calculate first the distance between the nearest neighbor atoms, this distance dn. To do that, I can use the law of similar triangles that you may remember from your high school physics and geometry. And you can say that, okay, if this distance is 1/4 the side of the cube, this distance dn should be 1/4 the length of the diagonal of the cube. Okay. Now, what is the diagonal of the cube? If the lattice constant is a, what's the diagonal? It's a squared plus a squared. That gives you 2a squared by Pythagoras' theorem plus a squared. So it'll be 3a squared, right? And the diagonal will be the square root of that. So it's √3a, right? And if this distance from one atom to the second atom is 1/4 of a, this distance dn should be 1/4 of that, right? Everybody with me?
Yes.
Yep.
Okay.
Yeah.
So the nearest neighbor distance between these two atoms, assuming that they're solid atoms that are that far apart because they're physically touching each other, must be √3a over 4. Okay. So if I knew what the lattice constant is, I can back calculate distance. Okay. And then the radius of each atom would be half of that. So I calculate the size of a silicon atom as 1.18 angstroms. That's kind of the distance between the nucleus and the valence shell of a silicon atom. Once again, of course, it's a fuzzy concept. A silicon atom is not a solid sphere, but that's the kind of picture that we have. Okay. Now you can also calculate something called the packing fraction, which is what fraction of the space is occupied by these solid atoms and what fraction is empty. You saw a few minutes back that you could have large voids in between, right? Well, what is the volume of a sphere? It's 4/3 pi r cubed. I've already figured out what the radius is dn in terms of the lattice constant, right? What's the volume of the cube? It's a cubed. And interestingly, you'll see that the a cubes cancel out. So the packing fraction of a diamond structure, regardless of whether it's actually diamond or silicon or germanium, the ratio is independent of the actual lattice constant, independent of the type of the semiconductor having the diamond structure, and that's 34%. So roughly 34% of the space is occupied by these spheres, 66% is empty voids. Of course, even within these solid spheres, it's mostly empty space, but we pretend that they're solid spheres, okay? So this concept of packing fraction gives you an idea of how tightly packed these atoms are. Now, for different crystal structures, of course, the ratio would be different. And although we won't get into that much in this class, in E440, where we talk about fabrication, that becomes a very important parameter because that tells you, in some crystals, the atoms are very tightly packed. They may be harder to etch. In other crystals, they're more loosely packed, and so on and so forth, okay? But you can do the same type of calculation for a compound semiconductor like gallium arsenide. But now you have a problem because now the first atom is a gallium having a certain radius, but the nearest neighbor atom is arsenic, which has a different radius. So you can no longer say that the radius of the gallium or the arsenic is half of the distance between them, right? Because the two are going to be different, right? So how do you do that? Well, to do that, you have to go backwards. You have to first start with a pure gallium crystal. From its lattice structure, calculate the radius of a gallium atom. Then a pure arsenic crystal, get its radius. Now you get the distance by adding up the radii. And from that, you can back calculate to get what the lattice constant of gallium arsenide is, okay? You can calculate the cracking fraction and you'll get a slightly different number, close to 34%, but slightly different. So there's a typical type of problem that you can expect. Another typical type of problem that you can expect in exams or homework is calculating the volume density of these atoms, number of atoms per unit cube. Okay, so let's see what that would be in the case of, once again, the FCC structure with the basis of 2 atoms. I'm doing this because that is the most important case for us. All right, so let's see, how can I calculate how many silicon atoms per centimeter cubed I have in a silicon crystal? Oh, by the way, I wanted to make a comment. You know, in science and engineering, people typically use MKS units, meter kilogram second, but somehow in the field of semiconductors, you know, for historical reasons, people have stuck with CGS units. Okay, so instead of getting densities in number per meter cubed, you typically quote them in number per centimeter cubed, and so on and so forth. Okay, so as long as you're consistent and stick with CGS units, you'll be fine. But you know, sometimes you can be thrown off. So whenever in doubt, convert temporarily to MKS units and then back to CGS units and so on and so forth. Okay, but in most cases, if you just stick with CGS units, it'll be fine. And wherever there are traps, I'll point them out. Okay. All right. So I want to calculate the number of silicon atoms per centimeter cube. How do I do that? Well, one way to do it would be, you know, draw a picture of a unit cell, kind of count the number of atoms belonging inside the cube, and then divide by the volume. That's a, you know, complicated, difficult way of doing it. Okay. And plus, you're never quite sure what fraction of an atom to count, and so on and so forth. So the rule is, you first count the number of lattice points, not the number of atoms. And then whatever number you get, you simply multiply that by the number of atoms in the basis. Okay. So how many lattice points do I have? Well, I got the ones in the corner, 8 of those. What fraction of those count? 1/8, right? So 1/8 times 8, we already saw that before. But then you also have the 6 square faces, right? What fraction of those count? Only half of those count, right? Because this lattice point is shared between 2 near adjoining cubes, while these are shared amongst 8 adjoining cubes, right? So you got 1 plus 3, 4 lattice points. And therefore the number of atoms would be simply the times 2, because I have 2 atoms on the basis. I plug in the number. In the case of silicon, it works out to 5 times 10 to the 22 atoms per centimeter cubed. Now you might want to keep this number at the back of your mind. You know, this lattice constant of 5.43 and the size of a silicon atom and this atomic density. Try to memorize these numbers, because, you know, we are engineers. Because later on, when you talk about concepts of doping levels of, say, 5 times 10 to the 16 per centimeter cubed of boron, you kind of get a sense that, you know, what does that number mean? So that means that roughly 1, if I have a doping of 5 times 10 to the 16 per centimeter cubed, divided by the silicon atomic density of 5 times 10 to the 22, that's 1 in a million silicon atoms that is replaced by a dopant atom to get N-type or P-type doping. Okay, so it's nice to have these numbers at the back of your mind. You can do similar calculations for actual density in grams per centimeter cubed. So for that, you first get the number density, number per centimeter cubed, multiply that by the weight of an atom, and that is atomic mass, which is in turn the mass of a hydrogen atom, which is a fundamental constant. In the exams, by the way, I'll give you all the constants that you need, obviously, times the atomic weight. Silicon has many isotopes. If you choose the mass 28 isotope, you end up getting a density in grams per centimeter cube. Okay, so this is density in number per centimeter cube. This is density in grams per centimeter cube. So that's another type of problem that you can expect. The third type of problem that you can expect is densities not per unit volume, but densities, areal densities, number per unit area on different planes. How does that work? Okay. Suppose I wanted to calculate the number of atoms per centimeter square on this plane, say this 1, 0, 0 plane, which is shown shaded. How do I do that? Well, once again, you have to do the calculation in terms of the unit cell, okay? And figure out the number of atoms or points within that unit cell, taking right fractions into account. And now the ratios are a little bit different compared to the volume densities, okay? So how many lattice points do I have in this square? Well, I got the 4 corner ones and the one in the middle, right? Now, what fraction of this atom should count towards the square in terms of areal densities? And think before you answer that. Earlier, when you calculated volume densities, we said that the corner ones are surrounded by 8 cubes, right? So only 1/8 of those count for volume densities. But how about now for areal densities? What fraction do you think should count towards the square? Is it still 1/8?
Would it be 1/4
Just
for the ones
1/4?
that are on the
Exactly, 1/4. Very good. So think of this plane extending in all directions, right? So this corner one is surrounded by 4 squares, right? So only 1/4 of those count. Excellent. So it's 1/8 ratio in the case of volume density, or 1/4 for areal densities. I have 4 of those. So 1/4 times 4. How about the one in the middle? For volume density is only half of that counted, right? But for areal, what fraction should count?
1, the whole thing.
Yeah.
Excellent. Very good. So it's 1/4 times 4 plus 1. What is the area of the square? A square, right? So for 100, if you work it out for silicon, that's the number that you get, 6.8 times 10 to the 14 per centimeter square. Now you may want to work out some of these other numbers, just so that you know how these things are done. Okay. And once again, there's a good chance I'll give you problems like this for other crystal structures.
Is the areal density basically just the density on one plane? of the cube?
Exactly. Yes. Yeah. In this particular plane. But I could do it for other planes also, right? Yeah. So these were 3 worked out examples, very typical of what you can expect. Any questions? All right. Now, very quickly, I'll describe how crystals are grown in industry and how you make silicon wafers out of it. This is the latter half of chapter 1. Now, in this particular class, I'm focusing mostly on the operation of the devices, not so much on how the devices are made. So I'll go over this very quickly, and I'm not going to test you on this in the exams. Okay. Having said that, I'd like you to read through them very quickly. Okay. It's fun reading, I think. But we get a lot more in depth into these topics of, crystal growth and fabrication in EE 440. Okay. I'll also, like I said, at some point show you a video which goes through the whole device fabrication flow. Okay. All right. So how are these crystals grown? Well, to grow crystals, it's a chicken and an egg situation. To grow a crystal, you need a crystal to start from to act as a seed crystal. Okay. We have seen that crystals are nice periodic arrangement of atoms in space forming these nice planes. So if you have a nice seed crystal, single crystal, then I can attach additional silicon atoms by some technique. Hopefully we should continue the same crystal structure. On the other hand, if I started out with a random arrangement of atoms in an amorphous solid, I can't really, these atoms that I'm adding don't know exactly where to fit, right? So you always need a seed to grow a crystal from. So what you do is, for crystal growth, you first have to refine silicon dioxide. So you start with sand or silicon dioxide or rocks. You can go to the beach, dig up sand. You react that with carbon, and that reduces this material to form silicon. I'm not balancing the reaction. I guess I am. Okay, silicon plus CO2, where the oxygen is removed as carbon dioxide or carbon monoxide and so on and so forth. So you react in a very high temperature furnace, sand with coal or coke and things like that, and you get rid of most of the oxygen. It all still has a lot of impurities in it. So then you do purification called by a technique called fractional distillation. All of this is described in chapter 1, the second half, that you can read through. So you basically react that with hydrogen chloride, okay, to form things like SiHCl3. You then purify the thing by a technique called fractional distillation, and then you convert that finally back into silicon, pure silicon. That's called electronic grade silicon, but it's still amorphous. It's not single crystal. Okay. So next, what you do is you take this electronic grade silicon crystals, lumps, you put them in a furnace tube, which is what's shown on the figure over here in this cartoon view, which is basically a crucible made up of graphite with a silicon dioxide lining. And you break up these clumps of electronic grade silicon, which is very pure but amorphous, and you melt it by heating up this silicon above 1412 degrees centigrade, which is the melting point of silicon. And that's what I'm trying to show in this orangey glow. It's red hot silicon. Okay. And in that, you then take the single crystal seed, which should be a tiny region which has nice crystalline arrangements. Okay. And you momentarily dip it into this molten silicon, and you immediately pull it back so that this molten silicon is drawn out by surface tension forces. And as it's drawn out of this liquid silicon, molten silicon, it cools by radiative cooling, and it crystallizes, having the same orientation as a seed crystal. Okay, I guess I should show it down below. So I'm growing this crystal in the cylindrical shape below the seed crystal. Okay. Now, to make things uniform, as you pull it, you tend to rotate the crucible, and you counter-rotate the seed, the crystal that I'm growing. And then you ultimately get what's called a boule or ingot of silicon, which looks like a cylinder. Okay. That's meant to be a cylinder. Yeah. My artistic skills are very creative, as you can see. Next, what you have to do is, after you pull this crystal, and there's a lot of details that I'm not getting into that you should read, even though I'm not going to test you on it. You can dope the crystal by adding, say, boron, if I want to dope it p-type in the melt, and a certain ratio of that gets incorporated to make it p-type silicon, or you can dope it with a donor arsenic to make it n-type at the right levels, and so on and so forth. Okay, where the concentration in the solid is determined on the concentration in the liquid phase. The two are not exactly the same. It's given by a ratio called the segregation coefficient or the distribution coefficient. All right. After you do that, next you have to convert this cylindrical boule into what are called wafers of silicon. So what you do is you take some sort of a saw and you slice them into these discs of silicon. I don't know if you have seen silicon wafers. They're this round, circular, more or less circular shaped discs of silicon. You saw them. Now the sawing operation damages a lot of the surface, creates a lot of defects. You polish it using a technique called chemical mechanical polishing. You shape the wafers. There's a lot of technology involved that we discuss in great details in E440. In this class, because of time, I'm not going to get bogged down with that. Okay. So at the end of the day, then you end up with these silicon wafers, which are like these thin discs of silicon. And then you make your individual chips on them using a variety of techniques, which are described at the beginning of chapter 5 that I'll go through very briefly. All right. And then you make typically hundreds of these shapes, and then you can saw them into individual shapes that you then package up. Now, these wafer dimensions are becoming larger and larger with time. So current state of the art have dimensions of the order of 12-inch or 300 millimeter diameters. The next stage is supposed to be 450 millimeter diameter wafers. They're so large that jokingly people call them not silicon wafers anymore, but silicon frisbees. Okay, so you don't want to throw them around like frisbees because they would shatter. Now, going along with the brief discussion of crystal growth, once you have grown the crystal, the wafers, okay, which are then made up of this nice crystalline planes and everything. In some cases, you may want to add additional crystalline layers on top of that to meet different device requirements. And that process of adding thin layers of single crystal on top is known as epitaxy. Epitaxy. The term epitaxy means I'm growing a thin layer in an ordered fashion. It comes from a Greek word. Epi means on top of. Taxis means in an ordered fashion. So how do you do that? Well, I take the silicon wafers, in this case, indicated by the circles. I place them on the sides of a barrel-shaped object, which can be heated up. This is a graphite block in which slots are cut, and then I heat it up so that I do the reactions at high enough temperature of the order of 1,000 degrees centigrade. You flow in suitable gases and you react them with the silicon substrate and you deposit silicon atoms on top of that. Okay, so what gases do I flow in? There's different choices. You can flow in, say, silicon tetrachloride, and you react that with hydrogen, leading to the deposition of silicon atoms, and you have a byproduct of HCl, which is flowed out. Okay, or you could have other gases like dichlorosilane and so on and so forth. Okay, you can also do similar epitaxial growth processes for compound semiconductors. That's described in chapter 1, using special gases called metal organic gases. That's why it's given a name, metal organic chemical vapor deposition. So this would be things like metal organic compound like tri-methyl, 3 methyl groups of gallium, reacting that with arsine, for example, AsH3, and that will give you gallium arsenide. Okay. I'm going very quickly because, like I said, I'm not going to test you on this, but hopefully you'll be interested enough to kind of read through that to get general knowledge. You'll not be tested on any of this in the exams. Another way of getting epitaxy is by a technique called molecular beam epitaxy. Here, you don't have any chemical reactions involved as in CVD, chemical vapor deposition, but instead you simply evaporate the materials that I want to grow in a very clean environment, in a so-called ultra high vacuum environment where the pressure in the chamber is super low, 10 to the power minus 11 torr. Sorry. Now, just for calibration, atmospheric pressure, do you know what that is?
760 torr.
Yes, very good. So this is what, roughly 14 orders of magnitude better vacuum than atmospheric pressures, okay? So in that super clean environment, suppose I'm growing gallium arsenide, what you have is you have a gallium arsenide substrate, which would act as your seed. And then suppose I'm trying to grow an alloy called aluminum gallium arsenide. That's one of those ternary semiconductors that we mentioned in the last class. You'll have sources which can be heated up of aluminum, gallium, arsenic that are heated up so that you create vapors of aluminum vapors, gallium vapors, and so on and so forth. And then you have these shutters, which are computer controlled, which can move rapidly in and out of place. Because I'm in such a high vacuum environment, the mean free path of these molecules are going to be very, very long, hundreds of meters. Now, the chamber dimensions are a few meters. So these aluminum atoms or gallium atoms basically travel like bullets. There's no air molecules to bump into. And if this is kept at a suitable temperature, maybe 600 degrees centigrade, these atoms then move around on the surface and they attach to the right lattice sites. Okay, so that's another way of getting epitaxy. This shows an actual structure that was grown at UT in one of our labs, where not my group, but another professor grew this, where you can see this cross-sectional view and see this beautiful layered structure of gallium arsenide, aluminum gallium arsenide. This is known as a gallium arsenide, aluminum gallium arsenide superlattice. So these are artificial crystals that have very interesting electronic and optical properties that we'll describe later on. Okay. Any questions? All right, I think I'll stop at this point and start off the next lecture by talking about crystal defects and then jump into quantum physics, quantum mechanics. Any questions? Okay, see you Monday. Sorry, Wednesday, sorry.
Thank you.
Thank you.
Thank you.
Thanks, Dr. Banerjee. Have a great day.
Thank you. Goodbye.